Hello, welcome to Unit 3. I'm so excited to be in Unit 3, you guys, because we are finally talking about the heartbeat of all of chemistry. We're talking about the atom and the structure of the atom and what is so amazing about that structure that gives us everything here, life on Earth. So today's lesson is on atomic theory and the introduction to the atom. So the atom is the smallest possible unit of an element that can still exhibit the unique properties of that element. Now, I love to show this video every single year because I think that we take for granted how small an atom actually is. So this video I think is going to be a real fun hang for you guys. Okay, oh my goodness. I hope you were noticing the sliding bar across the screen showing the metric system of what we're actually dealing with in terms of size. So you saw that carbon atom, it was about 1 nanometer big. That is so small. A nanometer is 1 × 10 to the 12th of a meter, which is crazy, you guys. And then even to get smaller into that, to look at the neutrons and the protons inside of the nucleus, we were dealing with femtometers. I think I said nanometers for the atom. I think it's picometers. That's even smaller, right? The 10 to the 12th. And then femtometers is what we were dealing with when we're looking at the subatomic particles. Anyways, so guys, I like this little comparison here. So the number of atoms that are in a grapefruit would be equivalent to the numbers of blueberries that it would take to fill up the entire Earth. So that is so small, y'all. And as we know, atoms are the building blocks of all matter in the universe. Okay, hopefully this is review for you guys. Hopefully the terms protons, neutrons, and electrons are not new for y'all. Protons, as you can see, are positively charged, and they are in the nucleus of the atom. Neutrons are negatively charged. Oh, no, neutrons are neutrally charged. So this blue thing right here is also in the nucleus of the atom. And then my electrons, which are on the outside of the nucleus, are negatively charged. So all elements have these 3 subatomic particles, but different elements will have different numbers of these subatomic particles. And as a result, this is what causes the variety of properties shown by all of the different elements on the periodic table. So what we're actually going to be doing a lot today in our notes lesson is we're going to be bouncing down to our handout, and there will be some places for you guys to actually draw some pictures, specifically when it comes to we start learning about how the model of the atom was developed. This is not a specific model, but this is a great standard representation to show us where these different subatomic particles are found within an atom. So what I've drawn right here is I've drawn a proton, and I want you guys to draw that right now in your notes. We're going to give him a P with a little superscript plus sign. That means that that proton has a plus charge, positive charge. And then also next to the proton, we're going to put a neutron with a little n and a little superscript 0. That just means he has 0 charge. And then we have an electron that is outside of the nucleus. He's a little e with a superscript negative sign because the electron has a negative charge. Please also label each one of your subatomic particles with what name it is. And then the last thing I want us to do is in some way specify that the nucleus is where the protons and the neutrons are, right? And the electrons are going to be outside of that nucleus. Right, moving on because I'm getting excited. Okay, so we talked about protons and neutrons. We're dealing with femtometers, itty bitty, teeny freaking tiny. With the atom, we're talking about picometers. Oh my goodness. This is a picture of a sheet of a gold nanoparticle. A gold nanoparticle is made up of a bunch of gold atoms. And I took this picture. Well, first of all, I did not take this picture, but whoever took this picture had to use the best of the best technology. This was an electron scanning microscope. And the way that an electron scanning microscope works to get pictures of very, very itsy bitsy teensy tiny things is it fires electromagnetic radiation or rays down onto a surface. And when it makes contact with the electrons on that surface, that radiation will be reflected back, and that is how you capture the picture. No matter, it is crazy technology that we're able to even get this picture. And the quality is not really that great. If you'll notice these little bumpity bumps, each one of those is a gold atom, but it's just kind of like the surface of what was reflected off of that atom. I cannot go in there and find my protons and my neutrons. We still cannot do that today, okay? So even with today's technology, atoms are still too small for us to study visually. So how did we discover, number one, how did we discover atoms? But then also, how did we discover all of those subatomic particles without actually seeing them? You guys, we have these scientists to thank. Our next topic is going to be atomic theory, which is the historical development of what we know about the atom from way back at the beginning of the time into what we know today. So these scientists, they would be on the Mount Rushmore of chemistry for sure. So our first main atomic model guy is going to be Dalton, and then we're going to talk about Thomson, and then we're going to talk about Rutherford, and then we're going to talk about Bohr, and we're actually going to wait to spend probably a full week on Schrodinger because he's got a real intense model, and it's one of my most favorite things to talk about. But we're going to talk about the first 4 guys first. Okay. So here's the thing about the atom. Since we're dealing with such small stuff, in order to develop the atomic theory of matter without the ability to see or touch, scientists relied on indirect evidence of how matter behaves in response to some experimentation. All right, so Democritus was not on the Mount Rushmore of chemistry here, but I like to bring him up because, well, first of all, he looks amazing. Look at that joyful smile. I mean, I would be happy too if I was theorizing about the atom. No matter. Also, every time you look up a picture of Democritus, he is always looking some version of this jolly. But he is back 400 BC. This is a long time ago. So let's see what Democritus had to say back in 400 BC. Oh, look, he's happy again. I love that for him. So Democritus was a Greek philosopher who first suggested the idea of an atom. He declared an atom was the smallest unit of matter, and an atom was completely solid and indivisible. If you see the word indivisible, it just means cannot divide up any further. Meaning this atom, whatever shape it may be, like I have pictures down here, he did not know what an atom actually looked like, but he said that, nope, you can't get anything inside of that is as small as it means. So this term atom came from the word atomos, which in Greek means indivisible. So that's basically what he said. It didn't really give us a model of what an atom looked like, but he said that there's got to be something that is the smallest unit of all matter. So good for him. That was in 400 BC, a long time ago, right? Fast forward many years after Democritus, we have John Dalton. And now John Dalton in 1807. Let's see what John Dalton had to contribute to the atom. So John Dalton was a British chemist who was the first to have a theory about how these atoms might look and behave. He had 5 parts of his theory known today as Dalton's postulates. Here we go, I'm getting excited. Okay, Dalton's postulates. The first one says that all elements are composed of tiny, indivisible particles called atoms. So kind of similar to what Democritus was talking about. So he's like, okay, here you go. That's what an atom looks like. Smallest unit of matter. I love that. Number 2 was all atoms of the same element are identical to each other. So here he has given you some oxygen atoms. They all look like the exact same red ball. So all oxygen atoms are going to look identical to each other. Postulate number 3 says atoms of different elements are different. Oh, so oxygen atoms are going to look different than nitrogen atoms. This is looking good so far. I like it. Okay. The fourth one says atoms of different elements can combine with each other in simple whole number ratios to form compounds. So here he's actually like talking about chemistry. Like, hey, I can take this atom of this element and this atom of this element, and they can come together in some sort of ratio of however many of one to the other to create a compound. We call that the law of definite proportions. There's going to be a whole number ratio of different elements to each other to make these compounds. And then postulate number 5 is that atoms cannot be created or destroyed during a chemical reaction. And the atoms of one element cannot change into atoms of another element. Guys, law of conservation of mass. Thank you, Dalton. He was the first one to kind of scratch the surface of that. He said, I can't just make an oxygen atom, poof, disappear. He can move himself around and rearrange himself with other atoms, but he can't turn into something else, and he cannot be created or destroyed. Wow, that's amazing. So with these 5 postulates, Dalton was the first one to give us kind of an idea of what an atom might look like. And you guys are not ready for this. There it is. There is his idea of the atom. He's like, okay, y'all, it's a ball. Which y'all are like, this is ridiculous. Well, Democritus didn't know anything. He was like, it could be a cube. It could be a starfish-shaped thing. But Dalton made the bold claim, it's got to be a sphere. Okay, spheres in science, I'm not going to get too much into this, are kind of a perfect shape molecularly and energetically, and Dalton had that foresight to be like, okay, it's probably going to be a sphere. It's called the billiard ball model. Billiard balls are pool balls, like playing on a pool table. So that's what we call his model of the atom today. Okay, I'm real excited. Let's see who is next. So that was in, what was it? 1807. I'm not good with dates. Y'all don't need to memorize dates. This is not a history class. But 1807, fast forward to 1897. We got J.J. Thomson. He's got his spectacles on, so you know he is ready to do some science. So Thomson was a British chemist who discovered the first subatomic particle, the electron. So the electron was discovered first, before the proton and before the neutron. Y'all, the electron did it. Okay, and he discovered the electron with what is known today as the cathode ray tube experiment. So here's a picture or a diagram of what a cathode ray tube looks like. And in preparing my lesson for today, I went back and was editing all my old lesson materials, and I had some videos about all these experiments that we're about to talk about today. And I was like, you know what? YouTube has gotten better in the past 7 years. I'm going to find some better videos of my cathode ray tube experiment. And no, I'm not going to give you a new video. I'm going to give you the same old one that I've shown every single year, and there is much laughter to be had with just the quality and everything that is to do with this. So please enjoy.
Late in the 19th century, in 1897, another scientist by the name of J.J. Thomson hypothesized that atoms are made up of even smaller particles. Thomson conducted experiments in which an electric current was passed through tubes pumped almost empty of air. You observe. What do you see when the electric current passes through the tube? You can see that light is given off. This light is created by rays traveling through the tube. Thomson observed that when a magnetic charge is introduced, the rays are deflected. Thomson reasoned that the rays were made up of negatively charged particles. Today, we call these negatively charged particles found in atoms electrons. Thomson also hypothesized that positively charged material existed in the atom. In his model of the atom, he proposed that an atom was made of a positively charged material in which negatively charged electrons were scattered. His model of the atom became known as the plum pudding model. He envisioned small electrons embedded in the atom, much like raisins embedded in a plum pudding. And about the same time, Henri Becquerel, Pierre Curie, and Marie Curie were learning fascinating things about the way certain elements emit energy in a process called radiation.
Guys, so let's talk about this. First of all, that video, amazing. I love the smooth jazz coming into the discovery of the electron. But okay, y'all, so this cathode ray tube was so freaking cool. So what we're looking at here when I get back to my cathode ray tube picture here is that basically a cathode ray tube is just a tube full of gas. Now, what we've discovered is that if you excite that gas with electrical energy, the gas particles glow to where you can see them, which is really cool. So what Thomson actually did is that he put on one side of the cathode ray tube a positively charged metal plate, and on the other side of the cathode ray tube, he put a negatively charged metal plate. So when he excited these gas particles and he had a beam of light that was running through, he noticed that those gas particles lifted up towards the positive plate. So with that, he concluded that, oh my goodness, there must be something negatively charged going on inside of that atom. So Thomson's cathode ray tube experiment showed that gases discharged electrical energy, light particles, when they were excited. Thomson saw that these particles deflected towards the positive end of the tube when they were placed in that magnetic field. This meant that atoms contained a negatively charged particle. So presenting Thomson's model of the atom. So they call it the plum pudding model of the atom. And plum pudding is kind of, I feel like, a dated word. I like to call it the chocolate chip cookie dough ball model of the atom. So basically what he said here is that, we're still dealing with a sphere, like Dalton told us, right? But inside of that sphere, we've got these negative chocolate chips, right? So we're going to draw some little circles inside and we're going to give them little negatives. Yep. And we're going to point to one of those guys and we're going to call that an electron. Yep. Now, in order for those electrons to be stuck in there, we know that different charges attract each other and like charges repel. You just can't have a ball full of negatively charged particles. They're going to explode apart. So he needed to have this buffer region, the sphere part of the atom to which these electrons were stuck to, had to have some sort of a positive charge. So we're going to call this positive charged sphere. Yes. Okay, so that's the plum pudding model of the atom. The very first subatomic particle that was discovered was the electron, and we know that electrons aren't really arranged in the atom like that today, but that's what he figured out in 1897, which is so cool. Okay, let's see. All right, so up next is Robert Millikan. He didn't discover a specific subatomic particle, but he built off of what Thomson's work did. So this is now in 1909. So let's see what Robert Millikan did. So Millikan was an American experimental physicist who determined the charge and the mass of an electron with this experiment called the oil drop experiment. And guys, let's talk about this for a second. I hope you guys know that the electron is the smallest out of all of the subatomic particles. And here we are discovering stuff about the electron first before we have any idea that the nucleus even exists. I find that so super cool. So I have another really fun video for us to watch here. So this is on what Millikan's oil drop experiment looked like, which is fun.
(1897). Later, R.A. Millikan looked to determine the charge on the electrons. The famous method that he devised between 1906 and 1914 to measure the charge E of an electron is known as the Millikan's oil drop experiment. Using this method, he calculated that the charge on an electron was about 1.6 times 10 power negative 19 coulombs. In the Millikan's oil drop method, an atomizer produces oil droplets in the form of mist, which are sent through a plate of electrical condenser. There are different forces which act on the oil drop, including gravitational, electrostatic force due to electric field, and viscous drag force. The rate at which these drops fall were measured by observing them through a micrometer eyepiece of a telescope. X-rays were passed through the chamber to ionize the air inside. On colliding with gaseous ions, these oil droplets acquire charge. The rate at which these droplets fall can be controlled by changing the strength of applied voltage to the plate. With this experiment, he observed that the magnitude of electrical charge Q on the droplets is always a multiple of electrical charge E. That is, Q is equal to NE, where N is equal to 1, 2, 3, and so on. Using the value of charge of the electron, the mass of the electron, ME, was then determined by combining Thomson's value of E by ME ratio. The value shown is the value of the mass of an electron. Petroleum.
Okay, you guys. So let's talk about this. So this was like a super sciencey experiment. So if you didn't understand exactly how all of that worked, do not freak out about that. We are going to be just fine. But the oil drop experiment is just a beautiful experiment in nature. So basically what I have here is a picture. So he basically shot teeny tiny little droplets of oil into a chamber, and those oil droplets fell. And then he used an X-ray to kind of ionize the air around the inside of the chamber, and those electrons started to stick to the oil droplets and fall. Now, since he knew that electrons were negatively charged, he put this really, really large negatively charged metal plate underneath. Now we know those negatively charged electrons, as they're falling, probably do not want to get close to that negative plate. So he looked at them under a microscope and saw how quickly they were able to fall. He was then able to measure how many electrons each oil drop had on it in quantized amounts of electrical charge. Okay, so Millikan determined that the charge of an electron was quantized, which just means that all possible charges on those oil droplets were multiples of 1.6 times 10 to the negative 19th coulombs. And that, since they were multiples of that number, that meant that had to be the charge of just only one electron. He then used the charge to mass ratio, which actually Thomson discovered, to then calculate, okay, well then what's the mass of one electron? The mass of one electron is 9.1 times 10 to the negative 28th grams. That is so small. So basically what he did is he just harvested or utilized the electrostatic force, the fact that a negatively charged electron was falling, would not want to come into impact with a negative plate, and used the law of the charge to mass ratio to calculate the mass of an electron and the charge. That's so cool. I love it so much. Okay. So next after Millikan is this fellow named Ernest Rutherford. 1911, things are starting to move a little bit more quickly because we're getting excited about the atom, I feel like, and probably technology is getting a little bit better. Rutherford has my most favorite experiment in all of science. I'm so excited to talk about this with you guys. So Rutherford was a chemist from New Zealand who discovered the nucleus with an experiment called the gold foil experiment. All right, let's see what this gold foil experiment is. I'm really excited. Oh my gosh. And just like the cathode ray tube experiment, I got a really old, nerdy video for you guys to see, and it is still a good one, so you guys can enjoy.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Okay, you guys. So first of all, I want to point out whenever she says the nucleus is large, or most of the mass is in the nucleus, she uses the term massive. Massive does not mean big. Massive means it's got a lot of the matter inside. But every year kids are always like, what does that mean? It's not massive. But so the gold foil experiment, you guys, oh my gosh, I'm super excited. So let's talk a little bit more about the amazingness that was discovered here. So what happened here is Rutherford shot what's called alpha particles, which are positively charged particles, through a sheet of gold foil. Yes? So gold foil is made up of gold atoms. Keep in mind, previous to this experiment, we were thinking that atoms were still solid, right? We were dealing with Thomson's plum pudding model, which had, yes, negative electrons on it, but they were solid balls. So when Rutherford did this, he was assuming, yep, okay, it's just going to hit a brick wall, basically, of gold atoms. He saw that most of the particles passed through. Most went through. I thought we cannot go through a brick wall last time I checked. And then here's something even crazier. Some particles deflected back, or even straight back. You guys, so what we're looking at here is kind of a cross section of that sheet of gold foil. Y'all, most of these alpha particles, these positive particles, just blasted straight on through. So Rutherford is looking at this and being like, whoa, if we were going straight on through, this atom is not solid. In fact, most particles went straight on through, so most of the atom has to be empty space. And the ones that deflected at certain angles deflected, which means they tried to avoid whatever the thing they were hitting in. So that let him know that the part of the atom that does have mass in it has to have a positive charge, because we know like charges like to repel. So here I have a positively charged alpha particle trying to get away from a positively charged nucleus. Lots came out of this experiment. So he concluded that the main part of the atom's mass is in the nucleus, and that the nucleus is positively charged. And the third one is my most favorite, that atoms are mostly empty space. Now, when I say mostly empty space, let's pretend that my nucleus of an atom is like the size of an apple, okay? That means the rest of the atom that is empty space would take over probably a diameter of like 2 miles around where this apple is. So that's like 99.9999999 repeating part of the atom, part of the atom is empty space. And we're going to have a whole conversation tomorrow about this empty space and how wonderful I think that what that represents is. But wow, big things coming out of Rutherford's gold foil experiment. Wow, there's a nucleus. It's got a positive charge, and y'all, most of the atom is empty space. So now presenting Rutherford's model of the atom. We call his model of the atom the nuclear model of the atom. So on our page here for the nuclear model of the atom, we're just going to put a circle here. We're going to give that circle some positive charges. Now, he did not know anything about protons and neutrons, but he knew that there was a nucleus, and the nucleus had to have some sort of a positive charge. So we're going to label that guy the nucleus. And then kind of orbiting around in this area, we have just these electrons. So we're going to draw some negative electrons. So he hypothesized that these electrons were orbiting around like planets orbiting the sun in a solar system, okay? So these are my electrons. And the other main key thing that he discovered here was this empty space, which even next week we are going to learn that there's actually so much going on within that empty space, which is super exciting. But that is Rutherford's model of the atom, the nuclear model that he discovered from that gold foil experiment. And so that was in 1911. Let's see what is happening next. Niels Bohr, 1913. So we're moving quickly here. This is just 2 years later. What did Niels Bohr do for the development of our model of the atom? So Bohr believed that the Rutherford model needed improvement. So he was like, I get you there. Those electrons are around, you know, in the empty space, probably orbiting in some way, but not just orbiting randomly. He proposed a new theory that an electron is going to be found in specific circular paths, or energy levels around the nucleus. And we're going to watch another really obnoxiously old video, and you're going to love every second of it, on what Bohr's model of the atom proposed.
In 1913, a Danish scientist by the name of Niels Bohr improved upon Rutherford's model of the atom. While Rutherford proposed that negatively charged electrons were held in orbit by the positively charged nucleus, he did not describe the location of the electrons. Niels Bohr proposed that electrons move in orbits around the nucleus, and he proposed that these orbital paths, or energy levels, are located at various distances from the nucleus. Today, we refer to Bohr's theory as the Bohr model of the atom.
So Bohr's model of the atom. So he said, okay, yes, we're orbiting around the nucleus, but what we're also doing is those electrons are actually going to be in specific energy levels at different distances away from the nucleus of the atom. Okay, so the key thing that's super important about this is he had a model of the atom too. We call his model the planetary model. So on your notes handout, we're going to go down to the planetary model. Similar to the Rutherford model, we still got some positive charges in this nucleus, right? So we still got that nucleus. But instead of those electrons just orbiting all over, right, outside of the nucleus, we've now got specific energy levels, right? And we're going to talk a little bit later about how many electrons are in the energy levels and all that fun stuff. We'll also learn that actually does not super matter too much because we know a little bit more in depth about what is really going on here. But no matter, we have electrons in energy levels that are orbiting the nucleus. Okay, so this is the planetary model of the atom that Bohr hypothesized, which is super cool. So now we're going back to our slides here. I want to talk only a little bit more about this Bohr model of the atom because we're going to have an entire 2 days on this next week. But Bohr's theory of the atom stated that each electron orbit has a fixed energy called an energy level. The lower the energy level, the lower the energy, and the closer to the nucleus that you actually are. He also said an electron cannot exist in between energy levels. He said in order to move to other energy levels, electrons either have to gain energy or lose energy. Okay. In the Bohr model, to move from one energy level to another, an electron must gain or lose the right amount of energy. This is where a quantum comes in. A quantum is the energy required to move an electron from one energy level to another. The energy of the electron is said to be quantized. I'm going through that very quickly because we're going to have an entire lesson on this and you guys are going to love every second of it. So do not worry. We're going to talk more about this later. Let's move on. All right. Real quick notes at the end here because y'all, we have done a lot here on the discovery of the atom, but we still have not discovered 2 out of the 3 subatomic particles yet. And it is 1913. So Rutherford is coming back. He's feeling real inspired after his gold foil experiment, and he discovered the proton in 1918. He realized that every atom has a whole number multiple of positive charge in a hydrogen atom. But he also realized that a nucleus couldn't just be made up of only protons. First of all, these atoms that he was looking at were too heavy to have just protons in it. Also, if you just had protons, their positive charges, it would be unstable. It would break apart, right? So then we have James Chadwick. James Chadwick's like, I've got an idea. He discovered the neutron in 1932. The neutron has the exact same mass as a proton, which means it would add mass to the nucleus, but no difference in charge. And would also come to explain different isotopic forms of different elements. So you guys, we have these atomic models. We got John Dalton with his billiard ball model. We got J.J. Thomson with his plum pudding model. We got Rutherford, thanks to the gold foil experiment, we got his nuclear model. And then Bohr is like, what's up, energy levels? We got Bohr's planetary model. We're going to talk about this next time. I love it so much. Okay. All right. Now, Let's review some of these parts of the atom. This is probably the extent of your knowledge of atoms that you've had here coming into this chemistry course. So I'm hoping that a lot of this is review. If not, is new information, and it is always exciting information to learn again. All right, so we just learned about the subatomic particles. Protons are my positive particles that are inside of the nucleus. Protons identify which element an atom is. Let me show you what I'm talking about with that. We have a periodic table. We love our periodic table so much. You guys, our periodic table have these numbers up on the top of our element symbols that we have memorized for me, right? So those numbers, if you'll notice, 6 is carbon, 7 is nitrogen, oxygen is 8, right? So those numbers represent protons. So if I have 8 protons, I gotta be oxygen. If I have 7 protons, I gotta be nitrogen. So your protons are the ones that identify what element I am. Neutrons are the neutral particles inside of the nucleus, and electrons are the negative particles that are outside of the nucleus. Okay, let's see. So now we have the subatomic particles, you guys. Our subatomic particles have different masses and different charges. So on our notes handout, we have a chart here to look at, right? So on our chart, we have the symbols for my different subatomic particles. Let me see if I can focus here. Focus. Yeah, okay. So I'm at different subatomic particles. So my proton and my neutron basically have equivalent masses. And my electron, his mass is different. And his mass is different by a lot. So much so to where if we were to give a relative mass of these subatomic particles to each other, we would say protons and neutrons are pretty much massively equivalent, and electrons are basically negligible. So to prevent us from having to write this giant number every single time, we've adapted a new unit of mass specific for subatomic particles called AMUs, and that stands for atomic mass unit. So a proton has a mass of 1 AMU, a neutron has a mass of 1 AMU, and an electron has a mass of 0 because it is that small. And the charge of a proton carries a +1 amount of charge. A charge on a neutron is 0, and a charge on an electron is a -1 amount of charge. Very fun. So here's some definitions. When I say the term atomic number, I'm talking about the number of protons. I say atomic number, you think protons. I say atomic number, you think protons. You know what we talked about when we said the number of protons identify what element you are? Say hello to the atomic numbers on your periodic table. They are the big numbers that are on top of the element symbols. They tell you the atomic number, they tell you the number of protons. So that's atomic number. The next number I have to talk about is the mass number. The mass number is the number of protons and the neutrons. So it's called mass number because we said that protons and neutrons are basically the only parts of the atom that have mass. So we want to know the number of all mass-containing things. So it's everything in the nucleus. This is so important. You're getting excited because you're like, oh my gosh, my atomic number, there she is on my periodic table. Guess my mass number is 2. Oh no. Mass number is not on your periodic table. It is unique and specific to every single individual atom, okay? It is a whole number. It is not on your periodic table. This number on your periodic table we're going to talk about tomorrow, that's called the average atomic mass. But mass number is strictly me adding protons and neutrons together. So that's going to be a whole number, not on your periodic table. Here's another maybe new definition for you guys, an isotope. We have an entire lesson about isotopes, so I'm going to kind of breeze through it here today. But an isotope is an atom of the same element that has different numbers of neutrons. So here I have 3 examples of hydrogen isotopes. They are all hydrogen because they all have one protons. Remember, one atomic number is hydrogen's atomic number is 1, which means he must have 1 proton in order to be hydrogen. But the variation that you guys see here is this hydrogen isotope doesn't have any neutrons. This hydrogen isotope has 1 neutron. This hydrogen isotope's got 2 neutrons. So you can see atoms of the same element kind of vary in how many neutrons they have. They cannot vary in protons because that will change what element it is. But I can have different variations of the number of neutrons. Okay, now let's talk about neutral atom. A neutral atom is an atom where there is no net charge. And the way that you get no net charge is your two charged particles need to be present in the exact same amount. What that means is my number of positive charges, my protons, needs to equal my number of negative electrons. So here's an example of a neutral sodium atom. I know he's sodium because I see 11 protons. I can grab my periodic table and be like, sodium, where you at? There you are, atomic number 11. There's your 11 protons. Well, if he's got 11 positive things, he's got to have 11 negative things. So you'll see an 11 proton, 11 electrons. That means he's got no overall net charge. Now, neutral atoms are very common, but that is not always the case. Sometimes we do have a charged atom, and a charged atom is called an ion. So an ion is a charged atom, and that is any case where the number of protons does not equal the number of electrons. Okay? Now I have two different types of ions. I can be a negative ion or I can be a positive ion. A positive ion is called a cation. So a cation is a positive atom that has lost electrons. And then an anion is a negative atom that has gained electrons. So the key thing here is in order to become an ion, you got to pop off electrons. You cannot get rid of those positive protons. Those are in the nucleus. Those are there forever. But an electron, you can kick those off or you can grab some more of them. So in order to be positive from that, you have to lose electrons. And in order to be negative from that, you have to gain some more electrons. The way I remember the difference between cations and anions, I'm going to come back to this, is cations are positive. Yes? Cations are positive. And I remember that cats are losers. Not because they are losers, but that just helps me remember that cations become positive because they lose electrons, okay? So back up here, here's a picture of the formation of a cation. Here I have a sodium neutral atom. He is getting rid of an electron, and he has gotten rid of one negative charge, so that means the resulting sodium atom, or ion, is now a positive charge. Here I have anion formation. Okay, so here I have a neutral chlorine atom. He is gaining an electron. He's got one extra negative charge. So his ion is a Cl with a -1 charge. Okay, so cations are positive. You become positive by losing electrons. Now on my periodic table has a lot of this fun stuff that we talked about right here, right now, right? So on my element blocks, the number in the top is my atomic number. Once again, that is the number of protons, yes. We have my element symbol, we have my element name, and once again, guys, this is the average atomic mass. It is not mass number, so you may write that right here, not mass number. Not MN is what I like to say, yes. So you're like, well, how would we know to find the mass number? Well, I'll have to give you that information. And what that means is we do this cute little representation of what an atom of an element looks like with this symbol notation. Up here in the top left corner, we have a number 12. That number in the top left corner will always represent your mass number. Once again, mass number is protons plus neutrons. Down here in the bottom left, the number in the bottom left will always represent your atomic number. And once again, your atomic number is your number of protons. Okay, how many protons use positive charges. And then sometimes, not always, but if I'm an ion, I will have a charge up here. This charge lets me know if the number of protons and electrons are equal. If you see a charge, you know that they are not equal. And so this charge will let you know how many extra electrons you have, or how many more or how many less electrons you have than protons. So the way to calculate charge, you take the number of protons minus the number of electrons. Yeah? Okay, very cute, very fun. Let's go through some examples here. So we got some isotopes of different carbons here. And this is something that is about to be in y'all's future very, very, very soon. As I'm going to give you something like this, I'm going to expect for you to interpret this in terms of how many protons, how many neutrons, and how many electrons each one of these carbon atom has. I'm going to show you the answer so we can kind of go through them. Okay, this carbon atom, all of them have 6 protons. Where I am grabbing the number of protons from is this bottom left number. Here's a secret. I do not even need that bottom left number. If that bottom left number is not there and all you see is a C, you can grab your periodic table and be like, well, what would that number be? Oh, carbon high, you're 6. Okay, so I feel it's a little bit redundant to both include the element, a letter symbol, and the number in the bottom, because those will always match each other, but no matter, there it is. Okay, where we get creative now is figuring out the number of neutrons. The number of neutrons, we have to subtract the number of protons from the mass number. Once again, mass number is protons and neutrons. So if I know I have 6 protons, and this is my mass number, 12 minus those 6 protons gives me 6 neutrons. Now zipping over here, let's count neutrons over here. Mass number is 13 here. 13 minus 6 gives you 7 neutrons. And then finally, this last one, I have a mass number of 14, so 14 massive things in the nucleus. 14 minus those 6 protons gives me 8 neutrons. Now, the last thing to look at here is all of these atoms are neutral atoms. And I know that they're neutral because I do not see a charge up here in the top right-hand corner. And that lets me know that the number of electrons for all of these atoms have to equal the number of protons, okay? Now, the cool thing to look at here is I have just given you a wonderful example of carbon isotopes. Once again, an isotope is an atom of the same element. These are all carbons, but they differ in the number of neutrons they have. And as a result, you can see that represented in the differences in the mass numbers in this symbol notation. Very cute, very fun. So there's also, let's do another one real quick. Okay, and if y'all are like, I'm so bored, Sabaka, I'm gonna move on with if you can stop the video, we're gonna be doing this again tomorrow anyway, all day. But I'm looking here and I've got different oxygens, okay? So if I'm practicing on this one, I'm gonna go ahead and show the answers and explain it. So all of them are oxygen, so they all have to have the same number of protons, and it is 8 number of protons. Once again, here I gave you an example where the oxygen does not have anything in the bottom left, but you know it is oxygen. You can grab your periodic table and see that he has an atomic number 8 and slam the number of protons as 8 down on your page. So to find the neutrons, you subtract mass number minus protons. 16 minus 8 gives you 8. 17 minus 8 gives you 9. And then 15 minus 8 gives you 7. So these are all isotopes of each other because I got different numbers of neutrons. We love that so much. Okay. Now, these first 2 are neutral atoms, which means that they have the exact same number of electrons as they have protons. This guy right here, he's got a -2 charge. So he does not have 8 electrons to match his 8 protons. Okay, you can either solve for the charge by saying protons minus the electrons will give you that charge. Or this is how I do it in my brain, is I ask myself, okay, it looks like I have 2 more negative things in my atom than I have positive things. Well, I know I have to have 8 positive things. If I have 2 more negative things than the positive things, then that means I have 10 negative things. And we'll do lots of practice on this. So that's an oxygen ion. Same number of protons on its electrons as the other ones, but same number of protons, but the electrons are not the same. Okay, here's another way I can represent what an atom has going on inside of it besides my symbol notation. This is called isotope notation. It's got a little bit less information, but we have the name of my element, which once again, if you know the name of the element, you know its atomic number from the periodic table, you can figure out number of protons. And then it's got a dash here off to the side with the mass number. So if I were to give you this, you should be able to tell me how many protons, neutrons, and electrons an atom has. So for example, I have 2 different forms of potassium here. Now that 19 for the number of protons, I cannot see there as an actual number here. I have to find potassium on my periodic table. He is K, he is right there. And I see a 19 above him. That is how many protons he has, okay? Neutrons, I always subtract mass number minus protons. So I had to take this mass number of 40 minus 19, and that's where you get 21 neutrons. So this mass number of 39, subtract protons 19, gives you 20 neutrons. Now, in this isotope notation form, there's no way for you to know if something is charged or not, so it is not a good way at all to give you information about a charged atom. This is strictly used for neutral atoms, so there's no way for us to do anything else but assume that the number of protons is equal to the number of electrons in these cases. So that's our conversation on the atomic theory, the history of the development as we know it today of our discovery of the atom. We're going to practice all day tomorrow on practicing counting all these subatomic particles and representing different atoms in their symbol notations and their isotope notations. But I had a blast. I'm super excited. I love these scientists, and I cannot wait to see you guys tomorrow.